So, hi everyone, and welcome to this video on our discussion on integration by parts using partial fractions. So, in the past few videos, we've discussed integration by parts using a definite integral and an indefinite integral. So, those are your basic types, and we discussed how to integrate simple integration examples for those. But we also discussed techniques of integration, which generally revolved around two main methods, which is integration by substitution and integration by parts. Now, if we try to sort of get the answer using integration by substitution and integration by parts of a complicated rational fraction, such as this one here, we may run into difficulty. And that may be the case of wanting to use, okay, in those types of scenarios, we would want to use integration using partial fractions. So what exactly is that? So when the integrand is a rational function, or in this case a fraction like the one above, what we can do is integration, okay, that process may be performed by decomposing it into a sum of simpler rational functions called partial fractions. So essentially, this function here, this rational function here, we're going to sort of break it down into a sum of partial fractions or simpler rational functions, in which case we can solve these simpler rational functions using the basic techniques of integration. So it's about sort of trying to decompose a complicated function, a complicated rational function, into more simpler functions. And this method of decomposing a rational function is straightforward, okay? For as long as the degree of the numerator is less than the degree of the denominator. So if you notice the degree of the numerator, this is 1 because the highest exponent is 1. In this case, it's 2. So we have a simple case there. Okay, so say we have an example. So say let's use this example. We have 2x plus 10 over x squared minus 2x minus 3. Okay, we're going to follow a set of steps, and I hope you can follow along. And we're going to try to solve this integral here. So the first step is you factor the denominator. So the denominator is given as x squared minus 2x minus 3. So if you try to factor it out into two sort of terms, okay, this one will be, if you do x times x, right, that's equal to x squared. Then this is like, to get negative 3, that's like 3 or negative 3 times 1. So you can get two terms, which is x minus 3 and x plus 1. And you should be able to get that since this is negative 3x, this is plus x, so the middle term is 2x, which we have, negative 2x, which we have there. The second step is to set essentially the fraction. So we have, remember, our original function is 2x plus 10 over x squared minus 2x minus 3. And what we're going to do is we're going to break it down into the sum of two simpler functions, or in this case, two partial fractions. And this is the denominator of this one will be x minus 3 and x plus 1, right? But what will be the numerators? Well, we don't know yet. So we'll set them at a and b, right? We'll set them at a and b. So that's our fraction there. Then what we essentially want to do is to be able to solve this problem. We need to first solve for a and b. Then we can sort of get the integral of this and the integral of that, which would be far easier than getting the integral of that entire thing. Okay, so what we're gonna do is to simplify this, we're gonna multiply both sides of this equation. So we're gonna simplify by multiplying both sides by x squared minus 2x minus 3. So that will give you, so with this term, that will cancel this one out. So that's 2x plus 10. This one will be, so we have a times x plus 1, because x minus 3 is already here. And that will just cancel out, plus b times x minus 3. Right, so we have here in linear equation form this expression there. Okay, then What we're gonna do in step 4 is we're going to look for values of x that will eliminate the terms involving a and b. And what this will do is it will enable us to solve for the unknowns, which are a and b, so that we can complete the partial fractions with their numerators and integrate them to get the answer. So in this case, so if you look at this equation closely, okay, in step 3, when x is equal to, so notice this one, when x is equal to -1, okay, we find that we get, this is, if we substitute that to the equation, that's 2 times -1 plus 10 is equal to a times -1 plus 1 plus b times -1 minus 3. So we get here, uh, this is 8, because this one is -2, right? Equal to a times 0 plus b times -4. So this one will just cancel out. And we're going to get this one, which is a term which is -4b equal to 8. Then I divide both sides by -4. I get b is equal to -2. So I'm able to solve for b there. What about if I try and set this one equal to 0? So that happens when x is equal to, in this case, 3. Okay, so we get 2 times 3 plus 10 equal to a times 3 plus 1 plus b times 3 minus 3. So this is going to be 6 plus 10, so this is 16, equal to a times 4 plus b times 0. So that just cancels out. And you're going to be left with 4a equal to 16. Divide both sides by 4. You get a equal to 4. So you have now values for a and b. And what you'll want to do is you'll just want to substitute that to this fraction that we got here. So this goes like this. So we get 2x plus 10 over x squared minus 2x minus 3. Essentially, this is equal to 4 over x minus 3 plus -2 over x plus 1, right? Because those were the terms that we found. And we can now perform the integration. So the integral of 2x plus 10 over x squared minus 2x minus 3 dx, this is equal to the integral of 4 over x minus 3 dx minus the integral of 2 over x plus 1 dx. Right, and what I can do is I can factor out the constant. So this is 4 integral of 1 over x minus 3 dx minus 2 integral of 1 over x plus 1 dx. Then if you know, you can just 1 over x, something expressed to x, this is just, the integral of that is just ln x minus 3, right? Minus 2 times, same procedure, this is ln x plus 1. Plus an arbitrary constant because this is not a definite integration. So that's a quick overview of integration using partial fractions. And in the next video, we're going to deal with a case wherein the factors of the denominator are linear and may contain repeated factors. So thank you for your attention, and I'll see you in the next video.